Assalamualaikum and selamat sejahtera. My name is Abdullah from AS253 6B2. Today I'm going to choose the topic under Laser-Induced Spectroscopy or LIBS by referring to the article entitled Forensic Analysis of Commercial Inks by Laser-Induced Spectroscopy.
The examination of inks and toners is very important in any criminal investigation, especially involving documents. The most common forensic issues often deals with the alteration of original document. For example, a modified check amount or an added line on a contract or a false signature on a will. Forensic studies of inks mainly regard the discrimination from one sample to another and determining the deposition order or the writing sequence of intersecting pen lines on paper. Among spectroscopic techniques, ICP, AES, and ICP MS are not used for routine analysis as they are very costly and require maintenance and also involve sample preparation. In fact, these techniques are often used only when other instrument technique which more simple and faster and also less expensive cannot provide a definitive answer. Vibrational spectroscopies, which are Raman and IR techniques, are non-destructive and they have imaging capability, and they are based on instruments that are simple to use and no sample preparation required. Vibrational spectroscopy combined with chemometric data processing are commonly used in forensic examination. These techniques capable to identify the chemical structure of functional group in the inks, colorants, and resins, but their success in classification is limited due to similar functional groups present within many inks.
Laser-induced breakdown spectroscopy is an atomic emission spectroscopy for the elemental analysis in real time. To analyze a sample, almost no preparation is required, and it's done without contact. A high-energy nanosecond laser pulse is focused onto the sample surface. The high energy density of the laser light is creating a plasma. By absorbing the laser light, the atoms are ignited into higher energy states. Within some hundreds of nanoseconds, the electrons are relaxing onto outer shells. Then the electrons recombines to the inner shells by emitting light. After a few microseconds, the emitting process is over. The emitted light is collected by mirror optic and guided via fiber to the spectrometer. Light is dispersed by grating and prism on a two-dimensional sensor and converted into a spectrum. A spectrum can consist of thousands of lines. Each peak stands for an individual elemental emission line. The intensity of a line is related to the concentration of the present element. This allows quantitative analysis with prior calibration using reference samples.
In this paper, the researchers tested LIBS for all relevant issues in forensic examination of commercial inks, including the classification of pen inks on one paper type and also on a different paper types. The third analysis is determination of the deposition order of layers ink, and the last analysis is the analysis of signature and toners on a question document. The first set of samples consisted of inks from 14 commercial ballpoint pens and placed on one piece of printing paper. The inks were deposited by drawing manually a very close parallel lines inside an area measuring of 1 centimeter square. Before starting the LIBS measurement, the inks were left to dry for at least 4 hours. Each of the 14 samples was probed at 6 points, each distance for at least 1.2 millimeter, in order to exclude the area affected by the laser-induced shock wave and also the eventual redeposition of material ablated from nearby examined points. At one sampling point, 10 laser pulses were applied, registering the spectra after each pulse in order to monitor the in-depth distribution of the inks. For the analysis of commercial black inks on different papers, the second set of samples consisted of inks from the same 8 black pens and placed over 10 different types of support, including printing papers, notebook papers, envelopes, and recycled papers. This set contained 80 different samples, with each one measured at 6 different points, with 480 measurements. In the third analysis, the blind test consisted of 2 replicates of printing paper with 4 manually drawn lines by 3 ballpoint pens and 1 gel pen, as we can see at figure 1a. The line finishing with an arrow intersect with the other 3 lines. The goals of the LIBS measurement were to characterize the 4 lines and to establish the chronological order of the deposition of the inks at the intersections. One of the 2 replicates was exploited for the repeated measurement of the inks and the blank paper. In addition to the single spot analysis of the cross points, while the second sample was probed at only 1 point per ink and per cross, with the aim of determining the margin of error in the ink classification process. The last set contained 3 printed pages with 3 signatures placed by different pen. The full specifications of this question document are given in Table 2. Example of the examined signature before and after the LIBS measurement is shown in Figure 1b. In this case, the analysis was to verify if the same pen was used on all 3 pages by applying LIBS at only 1 point per signature, and also if the printing toners were the same on all 3 pages. The toner were probed at 6 points by carefully choosing the sampling points in order to minimize the visibility of the laser. Analysis of commercial inks on a piece of paper. The spectra shown is taken from the first black ink and the blank paper. From there, the paper contains high amount of calcium due to calcium carbonate, which is a paper filler. Other than that, the paper contains silicon and aluminium. The analytical lines used for monitoring the elements characteristic for papers and inks are listed in Table 3. The detected overall plasma intensity was generally weaker on inks. Therefore, it is observed that an increase in the line intensities from ink components in the spectra produced the second laser pulse, which is at the fixed position, which mainly ablated the paper beside the residual ink layer. As the paper support is always involved in ablation, the absolute line intensities from elements belonging to an ink depend on its local thickness and distribution inside the laser spot. Hence, to reduce the signal fluctuation from one point to another for one ink and to compare different inks, signal normalization is applied on carbon because carbon presents in both paper and inks. The deposition of ink on paper does not produce uniform layer, and the penetration depth is expected to be irregular, and researchers also tested if the black inks could be discriminated by applying principal component analysis or PCA performed using a statistical software. The model was built using the peaks of zinc, manganese, copper, plumbum, nickel, chromium, and ferrum, which is the first laser pulse, and included 6 measurements for each of the inks. The score for the first 3 PCA components were 40.8%, 28.8%, and 15%. Linear discriminant analysis or LDA classifier was applied, and the examined black inks were 100% correctly classified, which demonstrating the method capability to differentiate all of the ink when deposited on the same printing paper. Analysis of commercial black inks on different papers. Among 7 elements mentioned before, manganese and ferrum were found in 8 papers out of 10 papers. The absorption of the inks also changed from one paper to another paper, whereby a higher absorption is equivalent to a lower amount of ink in the top layer ablated by the first laser pulse. PCA analysis is applied for the dataset containing the total of 480 data points, where each of the sample 6 measurements were taken. As shown in figure 6a, after applying correlation analysis, it is possible to separate inks, the first, second, third, and the 7th ink completely, and the data show much greater scattering. And by applying LDA, confusion matrix table is obtained, where off-diagonal count indicate the number points incorrectly attributed to another ink group. Characterization of inks on cross point. The paper itself did not show the presence of these elements. The ink used to draw the arrow contained only copper, zinc, and a very low amount of lead, but its copper content was at least 3 times lower than in the other 3 inks. The first ink had the highest content of copper, zinc, and plumbum among the samples, while manganese and nickel were not detected. For the second and third ink, they had a very similar composition, and they contained all 5 metals. However, they could be differentiated through the much larger presence of manganese in the third ink. Therefore, the researchers considered the ratio R of the normalized line intensity after the first and the second laser shot as a possible parameter for discriminating the deposition order. From Table 7, it is evident that the measurement on a single ink lead to a decay of the normalized peak intensities during the first 2 pulse number. This measured change was higher for lead and nickel compared to copper. Based on the result, the first cross for second measure, the top ink contained less plumbum. For the measurement M1, the detected differences were insufficient to establish the deposition order. On cross 2, the first measurement identified lower content of copper and also nickel in the top layer, which were attributed to the arrow. The analog changes in measurement 2 were too small to be conclusive. For the cross 3, both measurements showed a large increase of copper content from the first to the second laser shot, indicating that the third ink, which is rich in this element, had been deposited first. PCA analysis is conducted on each pair of inks, probe 6 times, and on the corresponding crosses. The example regarding the first cross is shown in figure 9. Here, it might be observed that the 2 inks are well separated. The first measurement on the cross produces the value in between both after the first and the second laser pulse, meaning that the 2 layers were too thin compared to the laser ablation rate. In the second measurement, the first laser pulse partially ablated the underlying ink, and the corresponding point is in between the 2 inks. The second laser pulse reached the area in the plot that is characteristic for the first ink, leading to a conclusion that the arrow was deposited on the top. The analog PCA plot for the second cross in the first measurement indicated that the arrow was placed over the second ink. In the second measurement, for both laser pulses, the point in the PCA plot fell in the area of the second ink, meaning that the layer left by the arrow was locally very thin and placed on the top. This hypothesis is enforced by the point moving in direction from the arrow to the second ink. On the third cross, both measurements indicated that the first laser pulse ablated the arrow and partially ablated ink the third ink, while the second laser pulse brought to the composition of the third ink, which was placed first on the paper. Finally, in the blind test, where the arrow was placed over the other three lines, the approach based on the ratio of peak intensities after the first and the second laser pulses. It is correctly identified the deposition order in 4 cases out of the 6 cases. The remaining 2 cases were inconclusive. The other one was identified correctly by using PCA analysis, while the missing answer could be attributed to locally very thin ink layers compared to the laser ablation depth. Characterization of inks and toners on a question document. The goal was to determine whether the document had been printed by the same ink or toner, and whether the signatures were made by the same ink on every page. The LIBS analysis on the inks on the page 2 is different, as it contains 2 times amount of zinc to carbon ratio, and ferrum is present in the ink. On the second page ink, it has weak zinc and lead signals, which may indicate that the black ink on the second page is probably from different ink. From table 9, it is evident that the toner on the second page is different, as it does not contain titanium, calcium, or magnesium, but it has a high silicon content compared to the other toners. The blind test on the question document has revealed that the signatures in second page are different, and it was printed by other toner. For each analysis, it can be concluded that the first analysis of commercial inks shows the different content of copper, zinc, manganese, nickel, lead, iron, and chromium metals. For the second analysis, LIBS are able to discriminate 8 types of inks on different types of papers by using statistical approach such as PCA and LDA. For the characterization of inks on cross points, by applying LIBS depth profiling on the point where 2 lines, which made up of different inks, intersect with each other, it was possible to determine accurately the layering order of the inks. Lastly, for the characterization of inks and toner on a question document, it was possible to demonstrate a single point LIBS analysis the chemical differences in 3 inks employed, or for the signature at one of the 3 pages. Moreover, the repeated LIBS measurement can correctly discriminate the toners based on the relative contents of silicon, titanium, calcium, magnesium, and potassium.